Welcome to Lecture 5.7, the norm of a linear map. As we've seen, the norm of a vector measures its size or magnitude. The set of linear maps between two vector spaces, say x and u, is itself a vector space. We can add or subtract linear maps, or we can multiply them by scalars. So we can ask, what is a natural notion of norm on this vector space? In other words, given a linear map A, what is the norm of that? What does that mean? What would that represent? The determinant is one way to measure the size of a linear map. However, this won't work for several reasons. First of all, it's only defined when the domain and the codomain are the same space. And secondly, it can't be a norm even when these are the same spaces, because there are non-zero linear maps with determinant 0. And one of the properties about a norm is that the norm of any non-zero vector has to be a strictly positive real number. However, there are a number of approaches that will work. Let me quickly summarize two natural definitions, and I'll give details about both of these shortly. First of all, there's the norm arising from the inner product, defined by the inner product of A and B is the trace of B star A. Since we are working now with real valued vector spaces, that's just the trace of B transpose A. And I think we talked about this earlier in the class, probably when we talked about traces. But again, more on this shortly. Another way to define the norm of A is by the largest factor that A can stretch a vector. So I will formalize this later, but for now, just remember this picture. Suppose you're mapping, say, R2 to R2. I'll let you imagine what this looks like in different dimensions. Then the unit circle will get mapped to some ellipse, and you can ask, what is the length of this largest axis? In other words, whatever that length is, that is the largest stretching factor over all unit vectors over here. Before we go any further, let's recall the following definition from real analysis. And if you haven't taken real analysis, then don't worry about it. Just pretend I didn't say the word recall. So this is about the supremum of a bounded subset of real numbers. And one way to think about this is what we want to define is the maximum value of the set. But that may not exist. And there's two ways how that could fail. First of all, if we have an unbounded set of real numbers, like say the integers, then there's going to be no maximum element. But suppose we have a bounded set, then it might have a maximum element, but it also might not, because it might maybe this is 0 right here, and we got a bunch of numbers less than 0. Maybe we have an entire interval here, like a half open interval, so it contains this right endpoint but not the left endpoint. And then maybe we have a sequence of numbers that gets closer and closer to 0 but does not contain it. So maybe this is like -1, -1/2, -1/3, -1/4, -1/5, etc. This is not going to contain a largest element, but what it does contain is a least upper bound, which is called the supremum. So it's going to have many upper bounds. Like 1 is an upper bound of the set. So is 1/2. So is the 10th root of 2, etc. But there is always going to be a unique smallest upper bound. In this case, it's going to be 0. 0 is not necessarily, it may be in the set or may not be, but in general, it doesn't have to be. In this case, it's not. It is an upper bound of the set, and it is the least upper bound. So the way to think about this is it's what you want the maximum element to be. So it's either the maximum element or what the maximum element should be. Again, this always exists, and we write it as sup x. Moreover, if S is closed, which is just a topological way of saying it contains all of its limit points, so it does not have any holes like this where something might, so this is a limit point without defining that formally, then the supremum of X is simply the maximum of S. So you can take this to be the definition of closed, a set that contains all of its limit points. Let's now return to those two examples of norms that I showed you in the previous slide. Sometimes we call these operator norms. A little bit easier than saying norms of linear maps. So the first one, we can define an inner product on the set of linear maps from X to U by the inner product of A and B is the trace of B star A. Anytime we have an inner product, we get a norm. And in this case, it's called the Frobenius norm. So the Frobenius norm of A is the square root of the inner product of A with itself. So that's the square root of the trace of A star A. And in terms of matrices, this is the square root of the sum of the squares of the entries of A. This is something that I think I showed you a while ago when we saw traces, but it's worth seeing it again. If let me write what A star A is. So since we're only over real vector spaces, this is just A transpose A. So if A is A11, A12 up to A1n, and then down to AN1, AN2 up to ANN. So these are the columns of A. Then A transpose is just going to be the rows of A transpose, or the columns of A. So if you think about what the diagonal entries of this are going to be, well, this 1, entry is just the dot product of the first column, or this row with this column here, and what that is A11 plus A11 squared plus A21 squared plus AN1 squared, and now this 2 entry is just the second column with the second the second row with the second column, so that's just A12 squared plus A22 squared plus etc. And if you see what we're doing, at the end of the day, we're taking the squares of every single entry in here and adding them up. So it's sort of like thinking of this as an as a vector of size n squared. It's just the entries are arranged in a grid instead of one long column. So that's where this thing comes from here. I guess I don't really need this absolute value because I'm squaring it, but this formula is going to, but I'm writing it this way because this is how it will generalize when we deal with complex inner products. Notice, and this is important, that this definition does not depend on any inner product structure of X or U. Even though I define this in terms of a matrix, the trace does not depend on a matrix or a choice of basis. It's just easier to think of it this way. So this is fundamentally a property of the linear map, regardless of inner product and regardless of choices of bases. Let's compare this to the second example of a norm on A, which is the largest factor that A stretches a non-zero vector by. Clearly, this definition will depend on the inner product structure that we put on X and U, because that determines the norms. In other words, we are mapping a vector little x to a vector, let's say AX, let's call this U, so that this is in big X, this is in big U, and what we're doing is we are measuring the ratio of the length of AX divided by the length of X, and this first one is norm in U, and the second one is the norm in X. And so as we change the inner product structure on X and U, that's going to change this ratio and potentially change this definition. Let's write it down formally now. For inner product spaces X and U, the induced norm of A is defined as the supremum over all unit vectors of the length of AX. And this is equal to the supremum over all vectors of the length of AX divided by the length or norm of X. So first of all, we call this the induced norm because it is induced by the inner product structures of X and U, whereas this norm up here doesn't depend on any inner product structure. Finally, let me say a word about this equality, because notationally these things look different, but it's very easy to see why they are the same. So let me explain it several different ways. First of all, I'll explain in terms of a picture. And even though I'm doing R2 to R2, it's the same thing for between any number of dimensions. So the norm is the maximum amount that this unit circle gets stretched by. So this is length 1, and maybe this is something else. Now, clearly it doesn't matter if I, instead of taking the unit circle, maybe I take the circle of radius 2. That's going to get stretched by the same amount. So that's going to get mapped to this ellipse, and this scaling factor, this, say that this length over that length is the same as this length over that length. Suppose this thing like rotates and stretches. So the scaling factor, it doesn't matter what length unit circle you start with. Let's write this out formally. I mean, let's, I'm thinking now it might have been better if I just had written this as AE, to emphasize that this is a unit vector, and say E is length 1. So let's say that X is equal to K times E. Then let's compare the top and the bottom here. So A times the norm of AX is the norm of AKE, which is the absolute value of K times the norm of AE. And then the bottom of this is just the norm of K times E, which is the absolute value of K times the norm of E. And of course, these things cancel, and this thing is equal to 1, so we're just left with the norm of E. So in other words, instead of looking over all vectors, we just have to look over unit vectors. And then one last thing I should say is, I didn't mention it here, but these are different norms. This lives in U and this lives in big X. But we usually don't have to write that because I think it's clear from the context. But it's worth mentioning that the norms are different. So we can change one of these norms, in other words, change the inner product structure on one of these or on both of these, and that will change this definition of the induced norm. Henceforth, we will use the induced norm unless otherwise stated. Here is a proposition. For any linear map A from X to U, the norm of the vector AZ is less than or equal to the norm of the linear map A times the norm of the vector Z for all vectors Z in the domain. That's the first part. And let me explain this and prove this before we get to the second part. So this is one of those things, there's a lot of them in real analysis that just look like they're obviously true. They have to be true. But real analysis is filled with statements like this, and a lot of them are true and a lot of them are false. So this is actually less trivial than it seems. And one way to see that is this first norm, norm of AZ, lives in the codomain U. The norm of Z lives in X. And then the norm of A, this is a vector norm in the space of linear maps from X to U. So we have three different norms sitting around here, And now this is induced by the other two norms. But if you look at it this way, it definitely seems like something that we have to prove, something that we want it to be true, and fortunately this one is true. So let's actually prove that before I talk about part 2. Okay, so for this one, let's recall what the definition of the norm. So how about if I write it up here? The norm of A is equal to the supremum, or the maximum, over all unit vectors. Or actually, here I'm going to say non-zero vectors, so let me say, write it like that, of the norm of AX divided by the norm of X. And the reason why I'm writing it this way is because this looks more like this than the version where it's also equal to the supremum over all unit vectors of the norm of AX. So this is the maximum over all of these, which means if I take an arbitrary vector, z, which may or may not achieve this maximum, then this quotient is going to be less than or equal to this, which is the maximum. So in other words, let's take any z in X, then the norm of A is at least as big as the norm of AZ divided by the norm of Z. And that's because, again, it's equal to the maximum of this. So for some Z, it likely won't achieve the maximum. And that's exactly what we had to prove right there. So there's really not much to this other than just unpacking this definition. Now part 2, what's this about? So remember, way back in the beginning of this section, I think it was in the first lecture, corollary 5.1, we showed that the norm of a vector x is the maximum, or it's the supremum, but since we're over finite dimensional vector spaces, we can call that the maximum. We look at all unit vectors v, and we take the inner product of x onto v. So a way to think about that is we take the unit sphere. So x is sitting out here, and we take the unit sphere and we look at all possible unit vectors, and we project onto each one of them, and we say, where is this projection maximized? And clearly that projection is going to be maximized where v equals x, the normalized version of x, and this inner product of x and v is just that length. Okay, so this part 2 basically is this result, but with ax instead of x. And I say basically because we still have the norm of a linear map here rather than the norm of ax. So this says that the norm of A is the supremum or the maximum over all unit vectors x and v of the inner product of ax and v. So by corollary 5.1, what we can say, so again, this doesn't follow immediately from corollary 5.1, but if we take corollary 5.1 with ax instead of x, then what we get is that the norm of the vector ax is the maximum over all unit vectors v of ax and v. And this is almost what we want. We just want to replace this norm of ax with the norm of a. And it's pretty easy to do that. So if the left-hand side equals the right-hand side, we can do anything we want to both sides. We can add 1 to both sides. We can multiply both sides by 2. And one thing we can do is we can take the supremum of both sides over all unit vectors. Now, the left-hand side is, well, yeah, how about if I write that here? So take or apply the supremum of over all unit vectors to both sides. And if I do that to the left-hand side, I get, by definition, the norm of A. And if I do this to the right-hand side, well, the right-hand side is just a single number. It's the maximum over all possible values. This is a set of values, but the maximum is one value. So this is a number. So we are literally taking the supremum, or the maximum, of a single number, which is, so the supremum of the maximum, or the maximum of the maximum, is just this supremum itself. So I don't know if I really needed to write that. So this is literally just the supremum. So again, take the supremum of the maximum is the supremum itself. And once again, supremum and maximum are the same thing because we are in a finite dimensional space. So take the supremum over all x equals 1 and v equals 1 of a inner product of ax and v. So it really is not much more than taking corollary 5.1, plugging in ax, and applying the supremum to both sides. And that's that. Now before we move on, let me say a couple words as to why we even bother to prove something like this second part. And that's because what we will do on the next slide is prove a proposition, and part of that we will show that the norm of A equals the norm of the adjoint. Now think how hard it would be to prove something like this using this definition of the supremum, because A goes from x to u and A star goes backwards from u to x. However, if we use this condition right here, then it's very simple to just rewrite the inner product of ax and v as x a star v. Now because this is symmetric, we can write this as a star v dot x. And then if we take the supremum of this over all unit vectors, what we get is the norm of A star. Now, I haven't written down what I said, taking the supremum over all unit vectors, but hopefully you can see the advantage of a characterization like this, as different and strange as it may seem from the definition. It falls out immediately why these two things are equal, where that's not at all obvious using the standard definition. Here is that proposition that I mentioned on the previous slide. All four of these things look like they are obviously true, and they are, but we still need to verify them individually. None of these are all that hard. They just use the definition. So I'll go through them fairly quickly. So given linear maps A, B, and C, first of all, the norm of Ka equals the absolute value of K times the norm of A. So the way to think about this is if A is a linear map, then its norm is the scaling factor, so is the largest scaling factor over all unit vectors. So maybe this, if A stretches this out by a factor of 3, then what happens when we do 2 times A? Well, it's going to stretch it out by a factor of 6. I mean, that just makes sense in terms of the picture. So this is, what did I say? 2A is going to stretch this out by, not exactly to scale, to a factor by 6. Okay, so how do we do this formally? Let's write this down. So we just use a definition. The norm of Ka is the supremum, or the maximum, over all unit vectors of K times A times X. And now we can write this. So I'm not going to write the this thing below the supremum on all of these. I think it's clear that I'm retaining it. So we can pull out the K times the norm of AX. And of course I can pull this K out here. It's the basic property of supremums. So this is absolute value of K times the supremum over AX, and I should probably write, for this one I'll keep it, norm of x equals 1, and this is the definition of the norm of A. This thing right here is just that. So that's part 1. Let's now do part 2. So part 2, it looks like it should be true. And it's true for all vectors, and by that I mean let's take any vector x, then the norm of a plus b x we know is less than or equal to the norm of ax plus the norm of bx. So it's tempting to just take the supremum of both sides over all unit vectors, and that's basically, I mean, that is true, but you're technically skipping a step if you do that. So what we're going to do instead is just write the definition. So I guess I didn't need to actually write this in the proof, but I still am going to, just for context. So the norm of a plus b is the supremum over all unit vectors of a plus b x. And this is the supremum over all unit vectors. Now I can replace what I have right. I can replace this thing here with this thing here by putting a less than or equal to sign here. So I just write this as norm of ax plus norm of bx. And let me put parentheses here just so you can tell. And then a basic property of the supremum, which you may remember from your real analysis course, is that you can split this up as the supremum of ax. This is less than or equal to the supremum of ax plus the supremum of bx. And this is the norm of A plus the norm of B. And how I made this jump from here to here, once again, I'll let you verify this. It's a little bit outside, I don't want to say outside the scope of this class, maybe a little bit below it, is that the supremum of two sets, say A plus B, is less than or equal to the supremum of A plus the supremum of B. And when I say A plus B, I mean if these are sets of real numbers, I mean A plus B is the sum of all things in A and things in B. So I'm going to leave this as a lemma if you want to check it, but it's a basic fact from real analysis. So that's part 2. And then part 3, so 3 and 4 are actually easier than these things. These things are hard, but they do use the definition and some basic facts from real analysis. Let's do 3 now. Okay, so let's take any vector x, and let's recall what we just learned on the previous slide, and that's the norm of ax is less than or equal to the norm of a times the norm of x. So let's apply that here, but with c. So in other words, the norm of c ax is less than or equal to the norm of c times the norm of ax. And now we can apply that again right here and say this is less than or equal to the norm of c times the norm of a times the norm of x. So now we want to compare, so we have this, we don't really care about this middle term, we care about the left-hand side and the right-hand side. And this holds for all vectors x. So let's take the supremum of both sides. So let me write that down. So take supremum over all unit vectors of both sides. And this this thing right here becomes the norm of CA by definition. And this thing right here, well, this is always equal to 1. So for any A, so this becomes norm of C times the norm of A. And that's that one. And finally, this last one, I'm running out of room, but I think I can squeeze it in here. Let me just do that, as I basically gave you the outline of it on the previous slide. So the norm of A is the supremum over all unit vectors x and unit vectors v of the inner product of ax and v. And we can move this, I'm actually going to write this as the inner product of x equals the inner product of v equals 1. We can move the a to the right-hand side and write this as the inner product of x and a star v. And now since this is symmetric, we can write this. So it's the same supremum over all unit vectors. But I can write this as the inner product of a star v and x. And it doesn't matter that this is x and this is v, and now they've reversed. So by symmetry, I'm doing this over all unit vectors x and v, and this is the definition of the norm of that map A star. Okay, so that proves part 4, and that's the end of the proposition. On this slide, I want to turn our attention to the subset of invertible maps in the vector space of linear maps. This is not going to be a subspace because it doesn't contain the zero map, but I claim that it has a particular topological property, namely that it is an open set. If you haven't seen this before, don't worry about it. I'll catch you up here. So let's let X be a vector space with a norm, which may or may not come from an inner product. For a fixed vector x naught and positive real number r, define the ball of radius r centered at x naught to be exactly what you think it is. It's the set of vectors whose distance is less than r from x naught. We write that as br of x naught. So the little mental picture that I like to have with this is, it's just this. I just draw a circle around this. You know, this might be in some higher dimensional subspace. Doesn't really matter. And the ball consists of all vectors that are inside this. Sometimes we call this a neighborhood. A subset U of X is open if for every vector in U there is some positive radius for which the ball centered at U of radius r is contained in U. So let me give you some examples and some pictures. You are all familiar with the concept of an open interval. So an interval like this is open if it does not contain the endpoints, and it's closed if it does contain the endpoints. So why do we use this terminology? Because if you close your eyes and you pick any point in an open interval, I don't care how close it is to the endpoint, you can find a little neighborhood around it. So a ball of radius r on the real line is just an interval of radius r. So this little interval is entirely contained in this open interval right here. That does not hold for a closed interval. Namely, if you pick the endpoint, it doesn't matter how far you zoom in. If you put any sort of interval around that, some of it's going to stick out. So this idea of an open interval generalizes. It clearly generalizes in higher dimensional Euclidean space. Imagine what an open set is going to look like. It's just going to be some region or a union of regions that do not contain the boundaries. So if you have some point here, I don't care how close you are to the boundary, if you zoom in far enough, you take small enough radius, you can find a little ball which is entirely contained in a set. Now, if it contains some of this boundary, then that will not be open because you take a point on that boundary, and I don't care how small of a ball you make, some of it's going to stick out of the set. So if you take unions of open sets, you still get open sets because there's no reason that we need to, and this is an open interval, but if you have the union of two open intervals, it's still going to be open. And similarly over here, we can have multiple regions. Now, if we're in two-dimensional space here, what we cannot do is take the union of an open interval, say on the x-axis, because in this universe, a ball is 2 dimensions. So if you try to do that, then any sort of ball around this point is going to be out above and below this line. So open sets sort of have, so the shape of an open set has to be it has something to do with the dimension of the space without being too formal. Okay, so where we're going to go with this is I'm going to claim that the invertible maps in a vector space, or I should say in a vector space of linear maps, is an open set. Let's write that down and formalize it. I claim that the following theorem implies that the subset of invertible maps is open, even though the language doesn't use the term open. Let's read it, understand it, and draw a picture, and really unpack what this is saying. Suppose A is an invertible map from X to U, and B is some other invertible map. That's close to A in norm. So the distance between A and B is less than, so think of this as your radius. Call that R. So here's a picture of this. So here's A. And let's suppose that you consider the ball of radius R. So let me call this R equals 1 over the norm of A inverse. Now I claim that if B is any other linear map in this ball, that is what we mean when we say the norm of A minus B is less than this R. That means B is in here somewhere. Then I claim that B is an invertible. So what this is saying is if we have any invertible map, so first of all, these things are living in the space of linear maps from X to U. So if we have any A in here, we can find a little ball around this such that everything inside here is still invertible. So in other words, the subset of invertible maps is indeed open. Let's prove this. So how do we approach this? Well, it's not clear what the first step is going to be, but what I'm going to do is I'm going to call this map here C. So let me write that down. So let C be equal to A minus B. So think of C being idea is if A and B are close together, this is going to be a map that should have a small norm. That's what we expect. So, of course, this is the same thing as saying that B equals A minus C. And now what I can do is I can A is invertible, so I can factor out A. I can write this as A times I minus A inverse C. Maybe I should really just go in this direction because, of course, these two things are equal, but I'm going to have a chain of things here, and I'm not sure how I would parse this if I made this if and only if. Okay, so we're factoring out an A like this. And so now what? Our goal is to show that B is invertible. And we know that A is invertible. So if we can show that this thing here is invertible, if we want to show that this is invertible, then we're done. because B, being the product of two invertible maps, would have to be invertible itself. So let's write that down. So our goal is to show that I minus A inverse C is invertible. I should probably just say it suffices to show that this is invertible. Let me say that here. This suffices. Okay, so how are we going to do that? I think the easiest way is to take something in the null space of this map and prove that it's 0. So let's take some x in the null space of A minus A inverse C. And it shouldn't necessarily be clear where we're going with this. We're just going to see what happens and hopefully show that this x is 0. And we want to show that x is 0. Okay, so I don't know, what do we do? Let's take I minus A inverse C times x, which is equal to 0. And let's see where this gets us. So this, if we multiply this out, we get that A inverse C times x equals x. So in other words, this linear map A inverse C has norm at least 1 because it sends x to x. So it stretches x by a factor of 1. So thus the norm of A inverse C is at least 1. It might be equal to 1, but it might be bigger. Now what else can we say about A inverse C? Now look at this assumption. So the norm of C is strictly less than 1 divided by the norm of A inverse. So here's the key. I'm going to go up here because I think I might run out of room down here. So, but the norm of A inverse C we know is less than or equal to the norm of A inverse times the norm of C. Now, that's something that we proved a couple slides ago. Maybe it was the previous slide, I forget. But now the norm of C, which, what's the norm of C? By definition, it's this, which is less than 1 over the norm of A inverse. Look what we have. So this is strictly less than the norm of A inverse times 1 divided by the norm of A inverse, which is equal to 1. So on one hand, we have that the norm of A inverse C is at least 1, but it's also strictly less than 1. So that is impossible. So that means that no such non-zero x can exist. So I said I want to show x is non-zero. If I were to go back and rewrite this, I should probably say, suppose there existed a non-zero x. Here is a contradiction. So I'm not going to go back and rewrite that. I'll let you write this up on your own if you want to, but that's basically why it's true. And remember, all we had to show is that this is invertible, and that's what we did. So that proves theorem 5.16, this curious result, but what I really want you to take from this is that the invertible maps in any vector space of linear maps is an open set. Finally, I want to conclude this lecture with a definition of what a norm on the vector space of linear maps from X to U is, because there's a lot more than just the two that I showed you. So it's a function from that vector space to the real numbers, satisfying the following three properties. The norm of K times A is the absolute value of k times the norm of a. It's subadditive in the sense that the norm of a plus b is less than or equal to the norm of a plus the norm of b. It's positive, meaning the norm of a is strictly positive for all non-zero a. And then there's a condition that is not required, but some norms have, and you can prove more properties about them if they do have this. That, well, first of all, this requires x to be equal to u. In this case, we say that a norm is submultiplicative if the norm of AB is less than or equal to the norm of A times the norm of B. So this is a lot more interesting when you get into infinite dimensional vector spaces, things like Banach spaces and Hilbert spaces. There's a lot more possibilities when you have infinite sequences that are in your spaces rather than just finite n-tuples. So this is more of a topic in a linear analysis or a functional analysis course, so I won't say any more about this other than just giving the definition and saying, if you're interested, please go explore. Coming up next, we will stick with this real analysis theme and talk about sequences of vectors in an inner product space. We'll talk about what it means for a sequence to converge, for a sequence to be Cauchy, and concepts such as completeness and local compactness, which are things that the real numbers have. We often don't think twice about them until we take a real analysis course and we have to understand them and prove every detail. But a lot of these properties carry over to finite dimensional vector spaces over the real numbers. And those are important to understand as well. So we will prove some of those things, not from scratch, but using those known facts about the real numbers and extending those to vector spaces. So stay with us.